Hello everyone, I am Rafi Kumar Khoba from UQ Delhi Research Academy. Today I am excited to present our work, PEFTDiff Diffusion-Guided Transferability Estimation for Parameter Efficient Fine-Tuning. This work was done with my colleagues Zijan Wang and supervisor Professor Chetan Arora and Professor Masa. We are addressing a crucial challenge in modern transfer learning, that is efficiently selecting the best PEFT method. The motivation is simple: with proliferation of PEFT methods like LoRa, VPT, and adapters, it has become a non-trivial challenge to choose the right one for a new task. The gold standard is to fine-tune and test every single one, and which is clearly time-intensive and computationally expensive. We need an efficient PEFT selection method that can accurately predict the winner with minimal cost. A traditional transferability estimation was designed to compare completely different backbone like ResNet and VGNet. They failed to reliably rank subtle variation introduced by PEFT on the same vision transformer backbone. We uncover why previous transferability estimation method fails. They assume a simple, well-structured feature space. As you can see from the scree plot, compared to classical CNN like ResNet, which retains 95% of the variance with only about 7% of the principal components, PEF embedding are far more complex. PEF require 30 to 50% of the principal component to capture the same amount of variance. This substantially higher nonlinear geometric complexity of PEFT embedding is the key reason traditional transferability estimation are inadequate for this task. To overcome this, we introduced PEFTDiff, a novel diffusion-based approach. We leverage diffusion maps, a nonlinear technique that models feature relationship by capturing the intrinsic geometry of the data. This allows us to assess the geometric structure of the complex PEFT embedding without imposing restrictive assumptions. Diffusion map by first constructed by a graph where nodes are data points and edges encode local transition probability. We then simulate a random walk process over T-step where diffusion distance measures the similarity between the points based on the long-range connectivity, essentially capturing with both local and global feature structure. This is much more robust than relying on simple Euclidean distance. We approximate this diffusion distance using the transition matrix. Our PEF selection scores combine two components, both measures using diffusion distance. The goal is to see how well a PEF method improves on frozen backbone. First, the inter-class scores quantify how compactly feature embedding clusters within the same class are. Second, the inter-class scores measures the separation between different class means. Our final score is the linear combination of the two normalized change metric, which represents the overall improvement in feature quality space. We have evaluated PEFDiff on comprehensive visual adaptation benchmark that consists of 19 datasets. We curated a diverse pool of nine PEF techniques on VIT 16 backbone. The results are compelling. PEFDiff substantially outperform all the traditional estimation metric baseline. On an average, we achieve a tau of 0.631 on natural and 0.55 on specialized dataset, with an overall average of 0.517. As you can see from the table, we have a higher improvement with the baseline. Our evaluation confirms that the importance of both intra and inter-class score is important. And we say that, as you can see from the hyperparameter analysis, the diffusion step at t equals to 10 yields the highest correlation. While PEFDiff is a bit more complex than simple linear baseline, its core advantages lie in overall efficiency compared to the full fine-tuning. We have 200x overall speed up compared to exhaustive fine-tuning. Thank you for listening. To visit our project page, kindly scan the QR code.